Thank you. So we are going to start the next topic of lecture today, which is introduction to gate arrays and semiconductor memories. Gate arrays I have mentioned in the class several times. Okay, several times I have mentioned, and I don't think there is a broad scope of treating this particular aspect, gate arrays, which falls under CAD VLSI in detail, but I think that you should have a better, some better knowledge, some more knowledge about gate arrays than whatever I have discussed so far. And the rest of time today, I will also discuss quickly, introduce the semiconductor memories, which will be dealt with in details in the next classes. What is gate arrays? First thing is gate arrays. In the gate array approach, normally the whole chip, suppose this is a chip, this is a semiconductor IC chip. This is an IC chip whose size may be several millimeters to several millimeters, and today of course it can be even several centimeters to several centimeters. Typically 4 centimeter by 4 centimeter is a chip size of a big processor. Okay, a big processor, large processor containing million transistors, has got a chip size about 3 centimeter by 3 centimeter, 4 centimeter by 4 centimeter. But usually chip size are limited to 1 centimeter. Normally does not exceed 1 centimeter. Please remember this. In this particular chip, in the case of gate arrays, the chip area is partitioned like this. We keep some space at the outside. So first let me draw an inner square or inner rectangle. And these regions are made for called bond pads. These are bond pads, okay? That is always there. Any chip, the periphery, in the peripheral region, there is a number of bond pads. This is of course an old approach. Please remember that today even 64 pin is a very few number. Nowadays people are thinking of, in fact we have chips with much larger number of pins, and then you have seen perhaps that the pins are no longer coming from outside, but even from the central locations. So there are sometimes the bond pads are also distributed. But in most cases, let me tell you, the bond pads are located in the periphery of the chip, and then we keep some space like this over the chip. Say this is one region. So let me divide the whole chip in spaces like this. Okay. Similarly, at the center or somewhere, I can put some dividers also. Okay. The chips, the area which is said, which is indicated by the violet lines, like this. These areas, we can say there is an array of, there are arrays of nMOS and or PMOS FETs, transistors. In the case of NMOS gate array, all the transistors are NMOSs. Whereas in CMOS, there will be a combination of NMOS and PMOS transistors. Okay, so please see that I have divided the chip like this, as indicated here, where the violet regions, the violet shaded regions, I am saying that these are assigned for these areas where these are, in fact, these occupy maximum area. The chip is so divided that these so-called violet shaded regions occupy the maximum area, and there are an array of identical NMOSFETs, identical NMOSFETs or NMOS PMOS array, identical. Okay? So this is a prefabricated slice. I have shown only a chip, but think of the whole wafer, which contains hundreds of such similar chips, exactly similar, called step and repeat array in 2 dimensions. I am showing only one single chip out of the array. So please remember that this is available to the fabricator, to the foundry which is making the ICs in the form of large, today 8-inch diameter wafers, 6-inch, 8-inch diameter wafers, which contains an array, a step and repeat array of the same chip layout, same chip, maybe 100 in number or 200 in number or 50 depending on the chip size, wafer diameter, etc. I am showing you only single chip for the gate array, in which, excepting for a small region in the periphery, the rest of the region is partitioned in such a way that there, in most spaces, whatever I have shown by the violet regions, there are arrays of identical NMOSs or NMOS and PMOSs, okay? And intermediate between, so this one and this one, you see there are some spaces available. These are called horizontal routing space. This is horizontal routing space. Horizontal routing space, and there are also some regions which is meant for vertical routing. And another thing I forgot to tell you, that just between the bond pads and the active region, over this space, there is a space here. dense distribution, dense two-dimensional distribution of these transistors are there, and their all contactors are available. From the top, you know where are the source, drain, and gates are located for individual transistors. That information you have, and that is stored in your computer memory in the form of layout. What has to be done now? What is a big circuit? So far as this is, of course, the gate array is an entirely digital circuit. This is not an analog circuit. Entirely digital circuit. Digital circuit consists of a number of gates, basically a number of gates, either this static logic or dynamic logic, whatever you want, and simply some flip-flops, resistors, etc., etc. Now these gates, which may be a small gate or even which may be an ALU. It may be a small flip-flop, or it may be a large counter, or it may be a big shift register. Okay? These are the component blocks of a big digital VLSI. If I draw the block schematic of a big digital VLSI, you will find such different blocks in some very small gates are there. Similarly, large processors are also there. And therefore, what I have to do, I have to design the layout of different, we call them macro cells. These are known as macro cells or macros. Which are nothing but the different gates, flip-flops, ALUs, big things also, shift registers, counters, etc. So what I do, I just sit with a layout editor, because the layout editor knows the location of all these cells, of all the transistors, and what are the locations of the source drain gates. That information in terms of coordinates is available with the designer in the form of a computer data bank. All right? Now he makes use of several CAD tools called computer aided design tools. For example, he starts with a layout editor. What he does, he designs the interconnection patterns of a number of digital segments. You can say they called macro cells. Various gates, flip-flop, ALU, shift registers, counter, 4-bit, 8-bit, whatever capability is. So what I do, simply I make the interconnection of the nMOSes or N and PMOSes available on the gate array to produce these different functions, and this data for interconnection are stored in the memory of the computer, and we call it the gate array library. This is what is called gate array library. So gate array library is nothing but a library of the layouts of the different macro cells which constitute the full VLSI digital chip. Now ultimately, each such cell will be described by inputs, outputs, power supply, and so on and so forth. For example, let us consider the case of an exclusive OR gate. The exclusive OR gate, if I say that this is the block of an exclusive OR gate, XOR, it will have 4 input connections, A, maybe A bar, B bar, 2 input, for example. Exclusive OR, A bar, it will have 1 output connection, and it will have 1 VDD input and 1 ground input. Input means connections. Suppose you have seen the chip, the IC chip. So exactly it will be each subblock, each such macro cell, schematically on the layout, maybe I do not know what is there inside, but externally I can assign some location called pins, just like our pins in the chip. We also call them pins. That intrinsically, each macro is described by a blind box, which I am not supposed to know. A designer who makes the design in IIT Kharagpur in the CAD lab, he does not have any idea how the transistors are interconnected inside to form that exclusive OR gate. What information he has is as follows. He knows that it is available in the form of a box of more or less this kind of size, and there are some number of pins assigned, called pin assignment, on either side. Normally what is done is, while designing all the ALU, all the macro cells, we keep the vertical height the same. The vertical height of each block keeps the same, is kept the same. Only thing is horizontal width are varied. Maybe an exclusive OR will be of this size, whereas an ALU, this is maybe the size of an exclusive OR. It's a small gate. Whereas a 4-bit ALU may have a size like this. This is an exclusive OR, and this is an ALU, 4-bit ALU. What is normally done, the vertical height of the layout, in this particular area, the transistors have to be suitably connected to perform the ALU functions. Similarly, in this particular area, the transistors have been suitably connected to perform the XOR function. And these are finally described by how? Just in terms of some pin locations at the two sides. Some pin locations at the two sides. And there are certain rules. What should be the minimums? Normally, all these pins have some regularity. They are not arbitrarily located. This pin, what do you mean by these pins? Is nothing but some metal thing, metal leads in the form of thin film, not a lead like this, in the form of thin film, coming out this side and that side for the application of input, for taking out the outputs, and for applying the power, ground and VDD. This must be done for each individual thing. And I have all this data, how to interconnect the transistors to form such cells in the library of my computer, called CAD, one of the CAD software. It's called, as you know, that is called VLSI CAD environment. Then the data in the CAD library, I have got this. Then what I do, you just see exactly that I have done here. Suppose a VLSI, digital VLSI consists of 5 exclusive OR gates, 3 ALUs, 6 flip-flops, kind of thing. So what I will be doing, maybe I will place one exclusive OR here, but you see that this vertical size has been kept the same everywhere. And this is the region where I will put. But these are the regions where the pins are available. This is called placement. This is what is in the language of VLSI CAD is called placement. What I do, I have to call the different functions from the library and place them in these violet hatch regions, which has got a standard height and variable width. I can place them. You know that different macros, height is the same, width vary depending on the complexity. The least complex, the most simple will be the narrowest, most complex will be the widest. Okay? And they have to be placed in appropriate locations over these violet regions as indicated in the diagram. Again, let me repeat that your computer library is there where how the transistors have to be connected to implement this function, they are available. You just call the library, automatically the coordinates are shifted. You know that everything is referred to certain 0, 0, certain origin. But now if the same exclusive OR is placed here, that 0, 0 has to be shifted, the origin has to be translated. That thing is done automatically by the computer. Just there is a grid point array, etc. is available, and that's how you can place the different functional blocks. These are normally called functional blocks on the chip, and means that automatically in the founder you have the design for that, how to place the different blocks. Now the different blocks have turned out to be connected to perform the function, and therefore should you place them arbitrarily? This placement should be methodical, should be followed on the basis of certain CAD rules, certain algorithmic approach, and that is what is known as CAD software. Using the gate array software, which is available, gate array editor, gate array software, we place the different macro cells in appropriate locations in the so-called these violet mark regions, keeping in mind that I have to connect them either using a single level metallization or using a multi-level metallization. If it is a rather simple gate array, a single level metallization may solve the purpose. But for any practical gate array today, a single level metallization, why? Because if when I want to connect this with this and this with, there must be some crossovers. I want to connect this pin with another this thing available with here. But similarly, this one I want to connect with maybe somebody here. It may be necessary. So what I have to do, perhaps this one can be routed through this, through this space and brought here, the vertical routing space. But intermediate, I may have another such thing here, and this may have to cross both of them. Do you follow? So in that case, what has to be done is, I have to know, this is called pin assignment. I have to know which pins are to be connected, called net list. I make a net list where the pins of different, how the pins of the different sub-blocks or functional blocks are to be connected. That information is available and again stored in the computer. Now there should be some automatic routing. You know that you can start, if it is a simple thing, you can start by your own brain. That is just by sitting in the editor and connecting this way, that way. You can solve the problem. But as soon as you're thinking of some lakhs to millions of transistors, a very complex digital VLSI, you cannot. So there is a need for design automation. This is what is called design automation. Okay? By the design automation, you may connect the different pins according to the net list available with you, each other, through those spaces which are called horizontal routing space. And most of you will find practically it is a horizontal space. It is so designed it is a horizontal routing space which is most important. And there must be some vertical. That is for, we have also given some vertical routing space. So these are all interconnected appropriately. And only at the inputs and output there may be some dedicated cell. These are not gate arrays. Because gate arrays are very high speed functions. Whereas from the input-output, the power, it does not really bother much about the power dissipation. They are all very low power operation, high speed, low power, okay? Because ultimately you cannot consume a lot of power in your VLSI chip. But on the other hand, input-output, you have to, maybe depends on the signal level. You may have to amplify you have to enhance the power of the input signal. You may have to deliver more power at the output for buffering. Therefore, input-output cells they are not gate arrays. They are fixed amplifiers or gates. Inverters, okay, with appropriate power delay products, and these are located at the various locations, and we have to connect them via again the routing space to perform your in function. This is what is known as, in short, in fact we are not going to the details of gate arrays, this is in short what a gate array means. Gate array is called a semi-custom chip. It is a semi-custom chip. In this case, the foundry means the fabrication factory, has got the necessary software for personalizing the gate array. Personalizing means interconnecting the different transistors to form the different macro cells. That thing I do not have. It is only that is the international contract or trade secret. You do not. In fact, I tried to develop gate array in the laboratory for some things, small version. I found that whatever CAD softwares available in the VLSI CAD lab is totally worthless. I can't use them. In fact, only I use the editors, and I remember, and I developed in a laboratory some I2L gate array for a long time ago, big version. And there I had to develop all the macro cells independently, all the macros independently. Only I use the pin assignment. They normally say, because I use their layout editors, interconnect routing and interconnect the so-called, one is placement, subroute placement, the other is routing. These things I have used, but the actual how the transistors are being interconnected to form the different macro, this information was not available. So I made, because it was an I2L gate array, I developed something myself, means in our group we did it. And therefore, you remember, you see that actually foundry has got all the information for fabrication. What you are doing, you are simply designing, means you have the library of the different macro cells, you have the layout editor, you have the design aids for routing and space placement. You are using them ultimately to design this is called higher level, not the final level, the higher level design. And this has to be given to the company, the foundry. From that, there is an interface software. They will automatically convert them into masks. For what? Masks for what? Sometimes masked for only metallization. In the simplest gate array, they are only masked for only metallization they do. That means all the slices are prefabricated and kept with thousands of slices. In fact, millions of slices in big companies, they are kept prefabricated. Only thing, according to your order and whatever design data incoming to them, they are translating them into the mask for metallization. That's the simplest approach. But if you use only the mask, then do you know what is the problem? The actual gate array area utilization point of view is very poor, just like our PLA. Therefore, it is found that if there are two masks, two sets of one for contact hole etching, the other is for the metallization. If these two you can supply to the manufacturer, they can make more compact gate arrays. This kind of gate array, whatever I have described, the simplest gate arrays, but there are certain other versions also. I think you have heard of flood of gates approach. In that case, what is available? A flood of a large matrix of NOR gates. Just in a textbook, you know that any NOR gate and NAND gates are universal gates. You can interconnect them to perform any function. That is done. The other approach, which is now very popular, is called multiplexers. Use an array of multiplexers. It has been found that multiplexers are better than NOR gates or NAND gates for realization of digital circuits. So we call MUX arrays, the multiplexer arrays are available. So these are the second kind of gate called flood of gates approach. But the by normal gate arrays we mean the array of transistors. So this is a very, very brief introduction of the gate arrays, which are so common, so useful today in practical case. And as you know, gate arrays with programmability is available today. These are called field programmable gate arrays. The connection you can make yourself by using the antifuses, or by making use of memory elements, RAMs, or latches, which I told you, which can be reprogrammed also. Gate arrays which are permanently programmable, gate arrays which are reprogrammable, both are available. The permanently programmable are more dense, which use antifuse. I think I have discussed antifuse in some earlier class. By making use of antifuse, you can permanently program a gate array in your lab without going to the foundry. So after this, I think whatever few minutes I have, I will utilize for just introducing semiconductor memories. As you know that just like memories, which I'm sure has been introduced in earlier classes also, it can broadly classified into two. One is called volatile memory. The other is non-volatile. And the volatile memory can be divided into two classes. One is called sequentially addressed memories. The other is called random access memories. Sequentially addressed memories using shift registers. The other is random access memories using normal latch circuits. Whereas non-volatile memories, there are many versions. One is called simple ROM. The other is called PROM. Then electrically programmable ROM. And then I think you know electrically alterable or electrically programmable erasable, EEPROM, EROM. Electrically alterable EEPROM. Electrically erasable program, sometimes also called electrically alterable ROM. Now, you know that though semiconductor memories are very important parts of VLSI circuits today, but in actual use, the other kind of memories are more useful than semiconductor memories still today. What are the other kinds of memories? Starting from the very old days, you know, there are cards, there are paper, we call paper rolls kind of thing, punch, what is called? Punch card, paper tape. Then, of course, the other better things, for example, magnetic tape. Then the CD is very recent. Then discs, floppies, hard disks, as you know, floppies, hard disks, and then today the CD-ROM. These are all non-semiconductor memories. They are very, very useful for storing large volume of data. But what is their main problem? Slow. Therefore, whenever you need some memory online, that is for data processing, while processing the data, you want to put it in the memory and call it and kind of operations, very quick operations. Semiconductor memories are to be used. Semiconductor memories were not in a very big, you know, it was not that much matured earlier, but today it is very much matured, as you know. That earlier the memory capacity was limited to single chip. On single chip, it was only several 64 kilobit, around less than a megabit. But as you know today, that megabit DRAMs and even megabit SRAMs, 2 megabit SRAM. Recently, I was seeing a paper. 2 megabit SRAM is also very common. The technology is and I think you have heard of cache memory and all these things where the static RAMs are connected in such a way that you can really access to huge amount of memory, almost parallel to the other memory, non-semiconductor memories which are available today. So with this brief introduction, I'll stop today. Thank you.